Society in 1990 annual meeting. 10 U.S. and foreign patents. You listed in who's who of American inventors and society affiliations are American Nuclear Society, American Institute of Aeronautical and Astronautics, and also the Society of Automotive Engineers. I'd like to also point out that Dr. Brown has 2 patents. The nuclear battery is a patent that's also in your brochure, in your program. And the important thing to mention as well is that this patent is so valuable that Bell Labs Lucent Technologies decided to copy the patent. And they decided to make a replica that would fit into a digital watch for the last 25 years. You're about to hear about real breakthrough technology that I'm very happy to introduce Dr. Paul Brown.
Thank you. Thank you. Of course, as Tom said, I'm here to talk about beta voltaic batteries today. Specifically, I'm going to address the tritium battery. The tritium battery uses tritium as the isotope because it's relatively benign. The tritium battery is a thin film semiconductor device which produces about 30 microamps of current per square centimeter of area from a film only 4 microns thick. French rolled, these film foils may be packaged in any convenient form with an operating life of more than 10 years of constant duty. That's every hour of every day for 10 years under full load. The application of tritiated amorphous silicon as an intrinsic energy conversion semiconductor for beta voltaic devices is what I'm presenting here today. Analysis of the beta voltaic application shows an overall efficiency of 25% for tritiated amorphous silicon. A beta voltaic battery is a nuclear battery that converts energy from beta particles released by a beta emitting radioactive source such as tritium into electrical power. Common semiconductor devices or designs of beta voltaic batteries use a semiconductor p-n junction device that is either directly exposed to beta decay or is illuminated by photons created when betas strike a phosphor. These common beta voltaic batteries suffer from technical problems in that the directly irradiated cells suffer material degradation of the p-n junction, limiting the operating life to days, while the photoconversion systems are indirect and limited by efficiency to less than 1%. A limitation of the aforementioned beta voltaic batteries is the self-absorption of beta energy in the radioactive source itself. In order to reduce the self-absorption of beta energy, the radioactive isotope must be incorporated into the lattice of the semiconductor. Tritiated amorphous silicon is a novel thin film material where tritium, a radioactive isotope of hydrogen, is bonded with silicon in the amorphous network. Tritium has a half-life of 12.5 years, is overall a benign radiation hazard, and the pure beta decay of tritium produces a beta particle with a mean energy of 5.7 keV. Thin film contact potential tritiated amorphous silicon cells have been built. These cells, called tritium batteries, have a specific power of 24 watts per kilogram, a full load operating life of 10 years, and an overall efficiency on the order of 25%. Cheap, long life, high energy density, low power batteries. I first disclosed this technology and the method of producing tritiated amorphous silicon January of 1990. Today this technology is patented with additional patents pending. It's been verified and several institutions are now developing manufacturing techniques. The beta voltaic effect may be defined in simple terms as the conversion of ionizing radiation to electrical energy by a material or a combination of materials. Radiation that is absorbed in the vicinity of any potential barrier, say a p-n junction, a metal semiconductor contact, or an electric field, will give rise to separated electron-hole pairs, which in turn flow as electricity due to the Volta effect. Of course, this occurs to a varying degree in different materials and geometries. So then beta decay generates ions in the semiconductor, and those ions migrate across the voltage barrier in much the same manner as in a solar cell, with the radiant energy of the sun replaced by the emitted beta flux. The emitted high-energy beta particles from the radioactive source traverse the cell material, losing energy and creating electron-hole pairs. Those carriers within the diffusion length of the junction are swept across, contributing a current. The highest device efficiencies are achieved by choosing a wide bandgap material capable of absorbing high-energy beta particles without degradation. Further, it should be noted that device efficiency increases with increasing source energy and beta flux. The number density of electron hole pairs generated per second in a tritiated amorphous silicon film is given here by equation 1. In a tritium battery, electron hole pairs are generated within the intrinsic layer and are separated by the electric field. This device is analogous to a photovoltaic cell, and the current voltage equation can be written as shown here by equation 2. The beta-induced current is related to the generation rate of electron hole pairs, the size of the device, and the efficiency of the electric field in separating the charges. The beta-induced current may be expressed by equation 3, while the open circuit voltage is expressed by equation 4. The entrapment of tritium is particularly apt in this application as it is readily substituted for the hydrogen present in hydrogenated amorphous silicon semiconductors with good intrinsic electronic properties. Radioisotopes other than tritium may be used as a source of energetic electrons, as well as other forms of energetic nuclear radiation, such as krypton-85, for example. The betas in a tritiated amorphous silicon film can also give rise to beta conductivity that is of a similar behavior to photoconductivity. This beta conductivity can be written as shown here by equation 5. A tritium battery consists essentially of a tritiated amorphous semiconductor sandwiched between two dissimilar metals, that is, metals with different work functions. The beta-induced electron hole pairs are separated by the electric field present, thus giving rise to an intrinsic nuclear battery, which is similar to a beta voltaic battery but is powered by tritium decay betas rather than external electrons. Today we'll present a description of the properties and methods of preparation of amorphous semiconductor, concept and theory of tritiated amorphous semiconductor applications. All films were deposited using an ion sputtering system. Hydrogenation of amorphous silicon is essential as it serves to significantly reduce the defect nature of amorphous silicon by terminating a majority of the defective silicon bonds. Typically 10 to 25 atomic percent hydrogen is incorporated into amorphous silicon hydride to obtain a material with good semiconductor properties. The hydrogen is bonded to silicon and can be chemically stable to temperatures of 300 degrees C. Tritiated amorphous silicon can be deposited in the form of small and large area thin films onto a wide variety of substrates, electrically conducting or insulating, using low temperature processing techniques. Various ion sputtering plasma deposition techniques differ only by the form of excitation used and in the resulting range of operating pressure. All our thin film tritium batteries are produced here. The metals as well as the intrinsic layers were deposited using our ion sputter deposition system. This system consists of a substrate holder at one end with the there is a heating element directly behind that. And this is the target holder at the other end. The substrate holder can be heated to 300 degrees C and can be biased from floating to ground potential. Tritium was stored on a tritide on a depleted uranium bed and was released by heating the bed. The temperature of the bed was used to control the equilibrium partial pressure of tritium over the bed, and a micrometer valve was used to introduce the tritium into the chamber. The system was pumped with a turbomolecular pump backed by a vacuum pump. During the tritium depositions, the exhaust of the vacuum system went to a tritium scrubber, which traps the tritium as tritiated water. The entire deposition system is housed in a nitrogen glove box. The tritium content of discharged deposited amorphous silicon film can only be indirectly controlled via the discharge parameters and the substrate temperature. However, these parameters also affect other aspects of film growth. The relatively low pressure required to ignite a discharge allows co-evaporation of silicon to directly control the silicon-tritium ratio. In this design, silicon is evaporated by RF inductive heating of high purity silicon held in a fixture. This provides relatively uniform heating. Our tritium scrubber is a design modeled after the tritium scrubber in use at Lawrence Livermore. A tritium scrubber positioned after the two vacuum pumps is used to strip tritium from the chamber effluent by converting the tritium gas into tritiated water, which is collected in a desiccant. The scrubber consists of a stainless steel cracking chamber filled with catalyst, which is heated to a temperature of 1,000 degrees Fahrenheit to ensure combustion of hydrocarbons over the catalyst, including methane. The heat is provided by a tube furnace, which maintains constant temperature to within 2 degrees. From there, the effluent passes through a gas-to-gas condenser consisting of 20 turns of stainless steel tubing cooled by a fan. The cooled effluent and condensate then pass through 2 molecular sieves connected in series, each made of stainless steel and filled with desiccant. A centrifugal blower is attached to the outlet port of the molecular sieve to draw gases out and into the exhaust stack ventilation. A getter bed consisting of 800 grams of zirconium manganese iron, which is known as ST909 alloy, is positioned downstream of the centrifugal blower for the purpose of scavenging trace quantities of tritium before venting the chamber effluent. The scrubber system is configured so that the deposition process can be carried out in a once flow-through mode or with the process system isolated. Pardon me. Anyway, the latter is the preferred mode of operation where the chamber effluent gases are continually processed, yet the scrubber system volume is sufficiently large to ensure that the downstream pressure is below the required backing pressure for the turbomolecular pump. Here we have the short circuit and open circuit voltage curve for a typical tritium cell. The intrinsic tritiated amorphous silicon layer was formed by initiating a discharge and introducing tritium gas into the reaction chamber. The structure of the tritium battery was nickel foil substrate, intrinsic layer of tritiated amorphous silicon, and zinc. Fourier transform infrared measurements indicate that tritium atoms were bonded with silicon atoms. The bonded tritium concentrations were up to 25 atom percent. Tritium outgassing measurements were performed on the tritiated amorphous silicon films, and it was found that tritium was stably bonded in the film at room temperature up to 300 degrees C. Tritiated amorphous films are mechanically stable, free of flaking or blistering. They have good adherence to the substrate, and they may be simultaneously deposited onto both conducting and insulating substrates using a discharge in a tritium plasma. The silicon layer The silicon layer, sputtered in a tritium argon ambient at temperatures below 300 degrees C, results in a tritiated amorphous silicon film with the tritium concentration being variable from 5 to 30 atom percent, depending on deposition conditions. Thank you. The optimum tritiated amorphous silicon thickness is a trade-off between capturing all the beta energy and collecting all the generated electron-hole pairs. Most of the beta energy is captured in a 2-micron thick film. Tritium batteries display a damage mechanism the same as the well-known Stabler-Wronski degradation seen in all amorphous silicon photovoltaic devices. Stabler-Wronski degradation is driven by electron-hole recombination and manifests itself as a decrease in the carrier diffusion length. For hydrogenated amorphous silicon photovoltaic devices, the highest initial efficiency occurs for device thicknesses around 800 nanometers. But because the degradation in diffusion length, the highest stable efficiency is obtained for 350 nanometer thick devices. From a stability viewpoint, the maximum allowable tritiated amorphous silicon film thickness falls in the 200 to 500 nanometer range. The maximum usable thickness of tritiated amorphous silicon film is limited by the degraded carrier diffusion length and is too thin to capture all of the beta energy. However, good device design allows most of the beta energy to be captured in the semiconductor. The basic concept is to use a multi-layer stack with the intermediate pairs being thin enough to be transparent. The outermost metal layers are thick enough to act as electron reflectors. These films are typically grown at a substrate temperature of 200 degrees C with 10 to 30 atom percent tritium incorporated into the film. The tritium concentration may be increased by reducing the deposition temperature, but at a cost of a reduction of carrier diffusion length. Cadmium sulfide is a wide bandgap semiconductor with a density more than double that of silicon. The higher density will result in more efficient energy capture from the high energy betas. In general, wide bandgap semiconductors have been found to be more radiation hard than low bandgap semiconductors. So cadmium sulfide is an excellent choice. Beta conductivity is a phenomenon evidenced by the increase in electrical conductivity of a material after the absorption of ionizing radiation. This effect is attributed to the increased number of free electrons generated by absorption of the ionizing radiation. Of course, recombination of the charge carriers does occur. However, during the time these carriers are free in the material, the conductivity can be greatly enhanced. For material in which one type of charge carrier predominates, for instance electrons, the change in conductivity with the radiation can be expressed as shown here by equation 1. Beta conductivity gain may then be defined as the number of inter-electrode transits that can be made by an electron in a conductor before the beta-generated hole is eliminated by recombination. For this case, where one type of carrier predominates, the gain is expressed as in equation 2. For an intrinsic tritium battery consisting of tritiated amorphous semiconductor material, the maximum beta power per unit area produced within the intrinsic region may be expressed as shown here. The maximum power may also be derived and expressed as shown. Of course, with these factors, we may then calculate the efficiency. The concept of intrinsic power conversion is achievable in tritiated amorphous silicon semiconductors for the purpose of low power applications. Tritiated amorphous silicon was used to make contact potential battery or tritium battery with a specific power of 24 watts per kilogram and an efficiency of 25%. Specific power is a function of the power density and the half-life of the isotope used. Measurements indicate that tritium was stably bonded in the amorphous silicon network, and products based upon this technology are currently being developed. Now, at that point, up to now, I've just been talking about tritium batteries, tritiated contact potential cells. But there's a lot of interest in my my oscillator battery also. So we'll talk about nuclear batteries in general. Devices for conversion of nuclear decay to electricity are nothing new, and many types exist. The simplest form of nuclear battery is the primary cell, was first demonstrated by Moseley in 1913 and extensively developed by Ernst Linder for RCA. A radioactive source rests upon a feed-through insulator, centrally located, within a conducting spherical shell. Beta particles emitted from the source result in a charge deficit or positive charge on the source, while the collecting electrode acquires a negative charge, establishing a difference in potential theoretically equal to the energy of the beta decay. Power is then delivered to the load in the usual manner. For instance, using radioactive phosphorus, which is a pure beta emitter with a 14-day half-life and a mean energy of 1 MeV, 1 gram occupies 1 cubic centimeter of volume and produces a primary current of about 2 milliamps. Assuming 100% efficiency, the total electrical energy or power emitted is 2 kilowatts. Here we have several patents for nuclear batteries which have been classed within the 4 major groups for their types of conversion systems. These technologies are possible due to the electrical nature of alpha and beta disintegrations themselves. Here we have one of Linder's many patents assigned to RCA for the primary cell, as we discussed earlier. The electric current produced by any source of charged particles may be expressed as shown here. We see that the current is determined by the rate of particle emission and the charge on each particle. This may be modified for radioactive substances to show the electric current as a function of the beta constant, or the decay constant, in the half-life of the isotope used. This relation may then be expressed in amps per gram for a predetermined quantity of radioactive substance. It follows that 1 curie of beta particles equals a primary current of 6 times 10 to the negative 9th amps. This is a p-n junction cell, as I discussed earlier, or I mentioned earlier. These batteries were used in long-life, low-power applications such as pacemakers before the development of the lithium battery. This is the most investigated form of beta-voltaic battery. Of course, here we have Rappaport's first patent, which was assigned to RCA for the p-n junction battery. This is my patent for the oscillator or resonant battery. This technology is still under development. Although I have greatly improved the design and new patents are pending, we will now consider the operating mechanisms. Here are several of the nuclear batteries I've built and tested while with NuCell in Idaho, Oregon, and Canada back in the 80s. This is a schematic of the vacuum oscillator cell. We see the strontium beta source, a beryllium copper secondary emitter, a silver ribbon inductor, as well as the oscillation transformer. This entire assembly is then housed within a resonant cavity. Here we have a strontium-90 foil in the form of an annular cylinder. It's over on the right. In the center is just an aluminum drum, which the foil is to be mounted on. Now we've put the strontium-90 foil upon the mount. One of the end caps are in place. Now we have both end caps in place. This is just to hold the foil under the drum. And the strontium foil drum is then mounted on the end of a Kovar rod with a feed-through insulator. Here we have the components of the vacuum oscillator cell wired and ready for assembly. The beryllium copper foil is mounted on a Kovar rod. It's electrically insulated from the end plate. That upon assembly, this is about the strontium-90 foil to slow the primary betas and to emit secondary electrons. Next, the two-layer space-wound silver ribbon is put into place about the secondary emitter to collect the primary betas, as well as the secondary electrons, which are sprayed onto it. This is necessary to collect the charges in the high-voltage, high-frequency skin effect region of the conductor. Now the composite transformer is placed about the silver inductor, which is wired in series with a transformer primary. The transformer is an open-ended flux design with low damping, high Q properties. That is, it's an oscillation transformer. With a bit of vacuum grease and an O-ring, the central body is placed over the assembly. And now we have both end caps in place, and we're ready to put a vacuum on it. Here we have two versions of the oscillation cell on the test bench. This is the photo most of you have seen that was taken by the Idaho Statesman newspaper, and of course that was picked up by the Associated Press. Okay, now the way this actually works, to understand how the oscillation cell works, we must first look at the basic LC circuit. Theoretically, if an LC circuit were superconductive, an electrical impulse applied to it would oscillate between capacitive and inductive energy forever. However, in the real world, no such circuit exists, so energy is lost. By tuning the circuit into resonance, the only losses are the ohmic heating of the circuit itself. Consider a simple circuit with a voltage source, a load, and of course a current is passing over the wire. The battery provides the electromotive force, and consequently conduction electrons within the wire are set into a generally uniform motion. By definition, electricity is measured in terms of the number of charged particles, that is electrons, moving past a point in a unit of time, and we call this amps. Now we expose the wire to radioactive beta decay and observe what happens. The process by which a beta particle is absorbed is such that the beta particle collides with the molecular structure of the wire, knocking electrons free. This electron avalanche occurs until the beta particle has given up all of its kinetic energy and comes to rest. For a silver wire, a single strontium-90 beta particle will generate some 80,000 ion pairs within a distance of only 30 thousandths of an inch. An EMF is present across the wire so that these newly generated free electrons acquire a uniform motion, thereby adding to the number of moving charge carriers. That is measured in the real world as increased current. Okay. Here we have the simple circuit consisting of a battery, a load, and a section of wire exposed to beta decay. Bork received 2 patents relative to this simple means of current amplification. Now we apply the Bork effect to a simple LC circuit. Then through every cycle of the oscillation of which current is flowing, that current gets amplified by an amount proportional to the activity of the source and the applied voltage. All we need is an input of an amount of energy equal to the system losses to achieve a sustained oscillation. At this point we have a self-driven oscillator. Any energy contributed to this oscillating LC circuit greater than the losses must be removed through an impedance matching transformer, which yields high-frequency AC current to drive a load. Most of our experiments with these devices were operating between 40 and 400 kilohertz. This figure depicts the starting method employed, which involves the use of high voltage source to charge a capacitor of the tank circuit, which is then discharged to ground through a Class C amplifier at a rate equal to the resonant frequency of the tank circuit. A spectrum analyzer is used to monitor the activity within the tank circuit, and once a clean oscillation is started, the high voltage and Class C amp are removed. A moving particle has an amount of kinetic energy associated with it by virtue of its mass and velocity. If the mass and velocity are held constant, and we place a charge upon that same particle, then a magnetic field is generated by the moving charge that is carried along with it, all according to Maxwell's laws. Energy is stored in this magnetic field, and by integration we may show that this magnetic energy to be defined by E squared V squared over 3A. The charged ion in motion constitutes a current element of magnitude EU, and the magnetic field at any point from the sphere is given by the equation shown here. Now the presence of a magnetic field around the moving body implies that magnetic energy is stored up in the medium surrounding it. The energy stored up in a unit volume of a magnetic field is simply expressed here. By integrating the value of this expression over the region exterior to a sphere of radius A, the total magnetic energy due to the motion of the charged body is shown to be given by E squared V squared over 3A. Then the magnetic energy due to the motion is analogous to kinetic energy, for it depends upon the square of the velocity of the body. In consequence of the charge carried by the ion, additional kinetic energy is associated with it. If the velocity of the ion is altered, electric and magnetic forces are set up tending to stop the change of motion, and more work is done during the change than if the ion were uncharged. The ordinary kinetic energy of the body is 1/2 mv squared. In consequence of its charge, the kinetic energy associated with it is increased by the value E squared V squared over 3A. Oh, this is I'll stop here. We'll stop here and take questions because we want to cut this short, right? That's good enough. I'll wind up here. So we have solid state batteries that produce pure DC output. They're about 25% efficient, and we're loading those up with tritium typically. The AC cells are still under development. They do produce higher power, but those are not production ready yet. Sure.
What applications do you see in the future for your batteries, and where, if there are some happening right now, where are they?
Okay. The question was what applications do we see for these batteries? In the case of the tritium cells, small electronics where long life and accessibility are a problem, satellite power systems, remote repeater stations for some of the higher power stuff. For the low power stuff, using tritium, cell phones, portable electronics, portable computers, that kind of thing. We're currently talking to some large manufacturers with just that purpose.
What is the life expectancy of these batteries? How long will
Well, the working life is 10 years. The output. Oh, the question was what's the working life of these batteries? The tritium cells output is determined by the half-life of the isotope used. In this case, it's tritium, which has a half-life of 12.5 years. So that means, say, if it was a 1-watt battery, 12.5 years from now, it'll still be developing 5 watts. So for a band of stable current generation, they have a 10-year operating life. They will continue developing power for the next 20 or 30 years, but of course that drops off with the half-life of the source.
conditioning electronics with the outputs then?
Okay, you wanted to know if you need conditioning electronics to have a stable output, and the answer is no. They are a constant current generator, roughly for about 10 years. Yes?
You're talking about putting this in consumer electronics. I mean, is there a disposal problem?
Well, there really isn't. Tritium is currently used in FAA mandates that tritium lighting is used on all commercial aircraft. All the exit lights and runway lights contain tritium. Tritium-containing products are currently in the market. As I said, tritium is relatively benign. In its gaseous form, it does present a potential health hazard in that it could be inhaled and converted to tritiated water in the body. But even if that was the case, it only has a 2-day biological half-life. It only resides in the body for 2 days, and there are there's no known dose of tritium that causes any biological effects, no level of harm. That's why tritium products are so easy to get into the market. Yes?
You said that in the description of how the battery works, you said that beta particle hits the wire and then you get an avalanche. Did you say that electron production? Because I understand it would be that if a high energy particle hits the wire, you may see an avalanche of charge carrier production. But all that will do is give you a spike in your resistivity in this local spot of low resistivity for a little while. When you heat up the wire, you get a high resistivity result.
Okay.
I don't see how that generates any kind of electromotive force within the resonance circuit as a whole.
Okay. The question was when a beta particle impacts a wire, he sees that ionization is produced, but he only sees that producing a localized increase in charge carrier density, so a reduction in the resistivity in that local area. And the answer is yes, absolutely right.
Plus one additional charge.
That is absolutely correct. The only way those ions contribute any current is they have to be through what's called a diffusion link. There has to be a field and material combination such that I'm using a p-n junction as an analogy.
You have to treat it inside the junction?
Correct. Yes, it has to be done in the junction.
So what does all the coils do?
Again, the question is, if, how do I want to phrase this question? Was,
In your prototypes, do you have,
Okay.
do you have, in the central region, do you have p-n junction usually with tritium source? Or do you have,
No.
you just have tritium at the center, then you have it surrounded by coils?
well, actually, no. In those cells, we use strontium-90, and it's a vacuum cell. What we do is we,
Surrounded by coils.
well, it's surrounded by a silver ribbon, yes, a coil. So the beta particle from the strontium-90 passes through a beryllium copper secondary emitter that generates an avalanche of electrons. That avalanche of electrons is then sprayed onto the silver ribbon inductor, which is operating in a vacuum. That's how we collect the.
You have a vacuum diode.
Yes, well, to collect tens of thousands of ions generated by a single beta rather than one or two, which you would if you were just simply irradiating a wire.
That's different than the picture that was on the slide.
Well, depends on which slides, but yeah, the lay explanation uses just a simple wire exposed in air, and it doesn't work quite that simply. Yes.
Hi, I'm an amateur experimenter. I've been working with dissimilar metals as plates, 6 inches apart. Got a little bit of voltage out of there, but 2 quick questions. I've been using aluminum and copper because they're cheap and readily available.
Sure.
I'm now aware of the term beta conductivity, and I think I need a source to find the right metal combinations. Is that available in, say, the Handbook of Chemistry or something?
The work functions of all the elements are tabulated in the Handbook of Chemistry and Physics, sure.
Including beta conductivity, which I think is...
Well, beta conductivity, if you want to buy my book, I address the issues, but there's no place where that's actually tabulated.
Okay.
But I give you the mechanics so that you can calculate it yourself.
Great. Second part of the question, real quick. Sounds like from his and your question, we would want to take the secondary of the transformer, which captures the beta particles. We would want to put some sort of beta source in the secondary of the transformer, or that might be an optimal design, right?
Absolutely.
Okay.
Yes. Yes, absolutely. The question was, have we explored any other means of starting the oscillation than using a Class C amplifier? The answer is yes, absolutely. The material I've shown here, this is really a decade old. This is all stuff I was doing in the 80s. The stuff we're doing now is patents are pending, and we are talking with some large companies, Mitsubishi, Nokia. Basically, I'm not at liberty to talk about what we're doing now, but the stuff we were doing back in the mid and late 80s is all public information. Yes?
If you were to lower the work function of the metals significantly, how would that improve the efficiency of the design? Have you considered amorphous diamond films as possibly one material probability or possibility?
Okay, there were 2 questions. If you lower the work function of the material, how does that affect the performance of the cell? And the second question was, have we considered
amorphous diamond substrates or films to lower the work function?
And have we considered amorphous diamond substrates? The answer is you want as wide a band gap as possible. So ideally, what you want is a combination where you have a very high work function material, such as platinum, and a very low work function material, such as cesium. Problem is, in the real world, the cesium oxidizes and doesn't maintain that low work function. We've had very good results with a platinum. We use a platinum foil. Cadmium sulfide is the intrinsic semiconductor, and lanthanum hexafluoride as the low work function electrode. The diamond stuff, no, but I'm aware of some work going on in Canada where they're doing that. I believe in Vancouver.
So you need both high and low work function to get your large bank in.
You need a difference in potential, and the difference in potential is established by getting both a high and a low. If the two dissimilar metals are very close to the same work function, then your difference in potential is very low. Your efficiency is going to go away. It'll generate heat instead of electricity. Yes.
Well, just a point of clarification for the audience. I'm particularly fascinated with the fact that, on your 75-watt AC output, strontium 90 cell, and you say that the kinetic energy of the betas is 30 milliwatts?
Correct.
Okay. Just to be sure that the folks get that point. I'd certainly like to see.
Well, I know where he's going with this.
Just to clarify the point.
The oscillation cell, the larger power devices. What he's pointing out is the strontium 90 source we use. That's a 1.1 Curie strontium 90 source. The textbook energy available from 1.1 Curies of strontium 90 is 30 milliwatts. That's 30 milliwatts of kinetic energy. The cell you saw developed 75 watts. Several orders of magnitude greater energy than theoretically available. And toward that end, that's why I was discussing the actual magnetic energy carried by these moving charges, because that's not accounted for with their kinetic energy. Now that is my theory of operation. Just one moment. The accepted explanation. I'm not the first guy to notice that these nuclear batteries produce more electrical power than theoretically available. Corliss and others in the 50s and 60s, they called this the multiplication factor, and they simply applied it to or acknowledged that it existed and tried to explain it away by the ionization effect, the fact that a single beta particle will generate tens or hundreds of thousands of ion pairs. And the multiplication factor of these cells, they noted that for secondary cells, they saw multiplication factors on the order of 10 or 20 times, and some cells as much as 200 times. But in the p-n junction cells, they acknowledged that multiplication factors were on the order of 100 or 200,000 times. I've tried to go a step beyond that. I don't simply write it off as multiplication factor explains where this additional current comes from. I'm trying to go to the very root of the problem. And a moving charge generates a magnetic field. That magnetic field has energy associated with it, and by calculating the mean velocity of these charges, we can work backwards and figure the magnetic energy available, and it's in agreement within 5 or 6%. So I'm very confident that that's actually what's going on. You had another question?
Well, yeah, and that's unusual. I certainly never heard the notion that we get higher magnetic energy from a charged particle than kinetic in a singly charged particle at high velocity.
Well,
Kinetic energy at that point in time.
the statement is that.
The question is, but that's telling the truth or not? I mean,
Okay, well, I'd like to answer that. The question is, he's never heard of magnetic energy being greater than kinetic, and I agree. It's not in a.
singly charged photon particle.
Well,
That's surprising.
let's use the analogy of a particle accelerator. If you take a slow-moving particle and you want to accelerate it to speeds close to that of light, you have to pump a lot of energy into this particle to accelerate it. And all charged particle accelerators do is pump in magnetic energy. In this case, we're talking about radioactive decay. This radioactive decay is already moving at near light speed. So it has this huge amount of energy that it's carrying along with it. What we're doing is essentially a particle decelerator rather than a particle accelerator.
They quote, what is the figure for kinetic energy per beta? So when they quote that number, that includes any field energy that's in there. That's the difference between energy levels. That's,
Well, again, it's a game of numbers because I I use charged particle accelerator data to support my theory that that this because you can work backwards from the observed mass of an accelerated charge. You can work backwards and account for the energy available.
I don't know what numbers you're using, but the energy that you're seeing, okay, has to be coming from the radioactive decay, right?
Absolutely.
So you're claiming a specific discrepancy between what you see and what numbers?
I must point out that this is not what I see. It's all textbook stuff. It's charged particle accelerators all over the world exhibit this same data.
Let's give another person a chance to
You're
question.
making a specific claim after
We can talk about it more after I get out of here.
Last question. Inspector.
Yes. Sure.
I didn't get the part where you said it caused an electronic, like you used the word avalanche. What was the step right before that? You said it creates an avalanche of electrons.
The absorption of any ionizing radiation causes an avalanche of ion pair generation. It's just the absorption of the kinetic energy of the particle. Yeah. Okay, well, thank you.